All right, thanks everybody for joining the ELISA June seminar. Today we have Khalid Aziz, who is a senior software engineer from Oracle, and he's gonna talk about what is a page table and why should we care about it. So Khalid, take it away.
Okay, hello everyone. So as I said, I'm Khalid Aziz. I work for Oracle. I'm a kernel developer. For the last 20 or so years, I have been working on Linux kernel development. My background is in real-time systems, embedded systems, worked on large server deployments, some cluster computing, and even some network processing. I work in various areas of the kernel, but for the last 6-7 years, I have been working primarily in memory management. So that's what I'm going to talk about today. What we are going to talk about is on a computer system, you have got shared resources, one of them being physical memory, and that physical memory has to be shared across multiple tabs that might be running on the system. And the memory management subsystem in the kernel ensures that all the tasks have access to the resource they need, and their access to that resource is isolated from each other. So processes are safe from writing over each other or corrupting each other's data. So in the process of managing this shared resource of memory across a task, the kernel uses page tables. So we'll talk about what a page table is, how it gets used, how it ensures isolation across processes. Since we are talking about memory, and now we are going to assign memory to various tasks, we need to manage all of this memory. We have to allocate memory so everyone gets access to what they need. And then we'll continue to talk about when we have a task that are isolated from each other in terms of their memory access, but they want to share memory. How do we do that? Then I'll move on to talking about how does page table play into this memory sharing, and what are the next things I'm looking at in order to make page table sharing more efficient. This a lot of depth into the memory management system. Is fairly complex subsystem. I'll try to touch on the high-level concepts. I may not go into depth, but if I'm talking to a slide and something doesn't make sense, please do feel free to bring up questions before I start talking about the next one to make sure we understand what I've talked about so far. Okay, so with that, let's talk about what are the shared resources on a computer system. You have the core shared resources. There's, of course, the processor, memory. Tasks will typically have access to a network and a storage. So these are the core shared resources. But on top of that, we can have additional shared resources as well. Most systems will have some sort of peripherals, keyboard, mouse, cameras. And then very often, embedded systems especially will have additional sensors. They might have actuators, so they can control a mechanical system out there. So all of these resources are shared, and the kernel needs to make sure that everyone who needs access to the resources gets access at the time they need it. So as kernel implements this sharing, there are certain guidelines, philosophy that it follows to make sure all of the sharing is done the right way. The one core principle is that every task that's running on the system should be able to make forward progress. Without that, the system is really not doing much. So workload must be able to make forward progress. And while making forward progress, it's also important that the resource sharing be fair, so that you don't have a task that hogs memory all the time, or you don't have another task that just hogs the processor and others are starved. So the resource sharing needs to be kept fair across various tasks. And then on top of that, this access to the shared resources should be accurate. Accurate in the sense that if a task is sharing a physical memory with other tasks, when it goes out to read its memory, it gets a certain data back. When it goes to read the same location in memory again, it should get the same data unless it has changed. So the results must be accurate every time. And then the access to the resource should also be reliable, which is when a task has been assigned a resource and it goes to access it, the resource should be out there. There can be a slight delay in accessing a resource depending upon what the kernel is doing, but the availability should be 100% for the resource. And then, of course, this access has to be safe. You have got multiple tasks running on the system. They're all doing their own thing. They should not stomp upon each other. So in terms of memory, when a task writes some data out to the memory, another task should not be able to just write over it unless it has been given permission. So that memory should be isolated from each other. So every task access is safe. Now, we have all of these requirements of isolation across tasks when it comes to resources. But there are times when we want to break these rules knowingly by design. For instance, at times we want the resource sharing to be unfair in the sense that we have a critical task running. It requires more access to the processor than others. Or there's a critical task that's managing a large amount of data and it wants access to 60% of the memory while everyone else gets 3%, 5%, 8%. So the kernel, besides making sure the resource sharing is fair, it also has to make sure that if the workload has a design in unfairness, it supports that, and that the workload be able to get the resources it needs. And same applies to sharing. Normally we talk about isolation, but we also want to be able to punch hole through these walls between tasks and be able to share data. So we'll talk about how all of that is implemented. All of this, I hope, makes sense. Okay, so let's talk about physical memory. Physical memory on a system is just a set of contiguous storage slots. Each slot has an address, so we know how to reach it. And typically the address starts at address 0 and just goes on until the end of the memory supported by the processor. Now, we have extremely large number of these slots, and trying to manage each slot individually is very tough. It takes too many resources. So for the sake of making it a little easier for us to manage the physical memory, what we do is we take a certain number of storage slots and group them into a base group. And that base group is a physical page. So this physical page size is, of course, not fixed. It varies from architecture to architecture. And some architectures can even support multiple page sizes. So if we look at, say, x86-64, a base page size is 4 kilobytes, but you can have a 2 megabyte page and a gigabyte page as well. But we typically in the Linux kernel work with a base page size of 4K. So once we have taken this physical memory and divided it into pages, that becomes our basic unit of allocation. That's what the subsystem will manage. So you'll hear a lot about pages. Anytime we talk about memory management, we are going to talk about pages. And that's just our basic unit of allocation. We allocate pages, we free pages, we group them as pages. Okay, so let's take a look at what a physical page looks like. So over here, we have the full physical memory. And we have divided it into just series of pages. So page 0 all the way until page n. And then there is a physical address that shows us where to go to in this memory. If we were to zoom into one of these pages, what you will see is a page of a certain size. Say, for instance, on x86, it's a 4K page. You'll see 4K storage slots. And then if we look at what the physical address looks like for accessing a specific location on this page, we can spread the physical address into two parts. One part is simply an offset into this page. So let's say this is a 4K page. This offset will be 12 bits because you need 12 bits to address 4K storage slots. So we have a 12-bit offset, and rest of the address really becomes just an index into a page. So this is effectively a page number, or what we call a page frame number. The reason we call it page frame is because this physical memory may be sparsely populated. So there might be holes in the memory. And even if a physical memory is not populated, doesn't matter. The page frame exists. Page frame may be simply empty because there's no physical memory backing it. So that's why we refer to it as page frame. So the top part of the address is really just a page frame number. And then the offset is an offset into that page. This concept becomes important as we try to understand what a page table is. So, but basically, physical page, that's just how we deal with it. Frame number, offset. Okay, so now let's say we have a big chunk of memory on a system. We want to run multiple tasks on this system. Well, we are going to share this memory across all these tasks. And if we were to try to access the memory using that physical address, we have to make sure that each task has its own separate range and it doesn't step upon the other tasks. That is done sometimes with embedded systems where the system configuration is very well determined and fixed. But in general, it's not a practical approach to be able to split up physical memory and make sure nobody steps upon each other. The way we solve this problem, where we can run a varying set of tasks on a system without constantly having to worry about who is dealing with which physical memory, we use virtual addresses instead. And virtual addresses are just like physical addresses, except they exist in a virtual space. They refer to a virtual page and a virtual page frame number. So now what we can do is these virtual addresses, they don't have to be unique across tasks, because these virtual addresses will map onto a real physical address at some point. So a task starts up, it says, I want to access memory at, say, FF503867. It simply issues that virtual address. We will take that virtual address, translate it into a real physical address, and then go access the memory at the physical address and run this data back to the task. Now, if we were to do this translation in the software, it's going to slow down the system very, very significantly. And we don't do that in software. There's a piece of hardware on the processor that helps us do that. And that's a memory management system. MMU intercepts every address that's placed on the system bus. And it looks at it as a virtual address. It will find the corresponding physical address and then fetch the data from the memory using the physical address and send it back to the task that wants it. So doing it this way opens up a lot of possibilities for us. So for instance, when you have a virtual address that you're going to translate to a physical address, well, until a virtual address is used, you don't really need to have a physical page behind that virtual address. So as a result, now, even though, say, the address space of a task on x86 is 3 gigabytes, we don't have to allocate full 3 gigabytes of physical memory every time a task is launched. We allocate just as much as is needed. And when the task tries to access a virtual address which doesn't have a physical page backing it, that's when we can allocate a page to it. That's how we can afford to run a number of tasks on the system that will add up to more memory than is on the system itself. And it so happens that a large number of tasks will start out and they won't use all of their address space. For instance, we are looking at, say, the program BC, which is a simple command line calculator. It's very simple, very straightforward. It's a very small program, requires very little space. So it can theoretically access the full 3 gigabyte range of addresses, but it never does. So we don't waste physical memory by allocating it to tasks that will never use it. And then as I will talk some more about it, we'll see it makes a few more options available to us in terms of how we manage physical memory on a system. Okay, so we talked about MMU does the translation from virtual address to physical address. So let's take a look at how it does that. So MMU sits in the middle on the system bus between memory and the processor. When a task is running and it wants to access memory, it will issue a virtual address, MMU traps it, translates it to a physical address, and then data is sent back. Now, what does that virtual address look like? Very much like what physical address look like. We again split it into, let's say, two parts. We'll take the simplest implementation of virtual address first. So in those two parts, one is the offset. The offset is again an offset into a physical page. And the size for this offset is going to be the size of a physical page. And then the other part of the virtual address simply becomes an index into a page directory. Page directory is just a series of entries. Each entry says this virtual address entry refers to this physical address. So when we see a virtual address, all MMU has to do is look at that directory entry index part of the virtual address, use that index to index into this page directory. The entry at that index gives it a physical page frame number. It takes a physical page frame number, combines it with the offset, and we get a physical address, which it then uses to access the physical memory and return the data. So fairly straightforward. So and now what we just looked at, this is simply a page table entry. And page table entry shows MMU how to translate from virtual to physical address. And a page table entry does contain the physical page frame number, which we use to then finally generate the final physical address. But page table entry can control more attributes as well. If there is a physical page backing a virtual address, there can be multiple attributes like, can the process read from it? Can the process write to it? Can we execute the code that's on that physical page? So all of that permission is stored in the page table entry. As I mentioned, a virtual address may not necessarily be backed by a physical page. Or if it is backed by a physical page, what can also happen is when the system is starting to run low on memory and it sees a page that is simply not in use, because a task very often will have a set of pages that they constantly touch, but a whole bunch of pages they go to very rarely. And so we see a page that's not in use heavily. What subsystem can do is actually squirrel away the contents of that pages elsewhere, which generally is a disk, and then allocate that page to someone else. So as a result, what happens is that that page, even though that virtual address did have a physical page assigned to it, but the physical page has now been given away to someone else. That is, the page is now swapped out. So as a result, the page table entry will contain these status bits as well. One, is there a physical page even assigned to this virtual address? Is the physical page assigned to this virtual address present in the memory or swapped out? Then we have other attributes, cacheability. You can even have security keys associated with each virtual page. So a process or a task must present the security key before it is allowed access to that page. So that's what a page table entry or PTE looks like. So when you have a collection of PTEs that cover the entire address range of a task, that's the page table for the task. And that's the purpose page table serves: controlling access, translating virtual to physical, managing the assignment of physical pages to each task. So now let's take a look at how manages these page table entries. If we look at a very simple page table entry, let's take just a 32-bit processor, one level a page table where you have 12 bits of offset for a 4K page, which means you have 20 bits of page directory index, which means your page directory has to have 2 to the power 20 entries, one for each virtual page. That's lots of entries. That's 1 million entries needed for just one level page table. It may not sound like a whole lot because on x86 32-bit, it takes only 4 bytes per page table entry. So that's only 4 million bytes to store the page directory for an entire task. That still doesn't sound much until you have hundreds of these tasks. And then that starts adding up. And we need to allocate a space in the memory to store all these page tables for each of the tasks. And the reality is, tasks don't always use their entire address space. But when we are looking at a linear page directory, it has to have a slot for each virtual page. So we potentially can have tasks where we are maintaining page directory with lots of entries being just empty. That's a lot of wastage. So we don't want to do that, especially as the number of bits in the address starts to go up. So when we go to a 64-bit processor, and if we were to follow this scheme, the size of the page directory is huge. So we have a solution for that, and that's solved by using multiple level page tables. And here's what a 5-level page table looks like. This is what is implemented on Linux kernel today. What we do is same thing as before. We take the 64-bit address, and this concept can extend to any number of addresses. If someday we have a 128-bit processor, we can just extend this concept. We start out again with an offset. That's the size of a page. And then next up, we have a page table entry. Then we have a page middle directory, page upper directory, page level 4 directory, and then a page directory. This page directory is same as what we had seen with a single level page table. But here's how things change here. When you take this top part of the address, the page directory index, you go to a page directory. The page directory will have one entry for each of the pages for page directory. So let's say each one of these is 10 bits. So we'll have 1,000 entries in the page directory. When we look at an address, we get the page directory index, we index into the page directory. This page directory entry simply points to the start of a level 4 page directory. And this page 4 directory index part of the address gives us an index here. And then similarly, once we get the index, that points to the start of the page upper directory for just this part of the address space. And we then look at the page upper directory index and use that to index into this directory to get the next entry, and so on. We keep going until we finally get to the page table entry, which we combine with the offset. This here now is the final physical page address, or the physical page frame number, which we combine with the offset to get the actual physical address. How does this help? Well, it helps because you have got 1,000 entries here. For each one of these entries, there's a potentially another 1,000 entry here. That's, I'm assuming each one of these is 10 bits. But if a whole section, like say we had an entry here, which has no physical pages backing any of these addresses, that entire 1,000 index page for directory for that one entry doesn't even have to exist. So we only populate that directories that need to exist because there is a physical page backing it. And since we have only 1,000 at each level for each entry from the next upper level, we can bring the number down to fairly small. For instance, if a task was using only 1,000 pages, we have to populate only one of these, and then there will be one of these for each one of them. So our overall space requirement drops significantly. So that's where the multi-level page table helps. Okay, so we talked about how pages are managed, and then we talked about we allocate pages and then manage them using the page table. So let's talk about how page allocation works in Linux kernel. So on the Linux kernel, the core allocator for managing the free pages is a buddy allocator. It's called buddy allocator primarily because it manages pages as sets of buddies. So it will group pages in numbers that are powers of 2. So for instance, 2 to the power 0, that's a single page all by itself. It's called an order 0 page. Or we look at order 1 page, where it will take 2 contiguous free pages and put them together in a group which will be an order 1 page. That's 2 to the power 1. So 2 pages make up an order 1 page, and this group of 2 pages is not order 1. Similarly, we go to order 2 pages, which will be groups of 4 pages. So buddy allocator, buddy is a pages with its contiguous buddy. So that's why we call it buddy allocator, and it actually brings in a whole lot of advantages when we manage memory like this. So for instance, some task comes along and wants a single page. No problem. We go to the list for order 0 pages. We grab a page out of there, done. But then another task comes along and it wants 4 pages. Instead of scanning the entire free page list to find 4 pages, we go straight to the order 2 page list. Grab a group of pages out of there, which will be a group of 4 pages. We just hand it off to the task. We're done. And you can see this effect of grouping the pages into orders of 2. If you were to say just run cat proc buddy info on your system. I have sample output here. So this is just one of the lines, sorry. This is just one of the lines from proc buddy info. What it shows here is this is the number of order 0 pages. This is the number of order 1 pages, order 2 pages, so on all the way up to order 10 pages. And buddy allocator and subsystem in general will try to collapse the contiguous pages as much as possible. So if it sees 2 order 2 pages that happen to be contiguous, it will promote them to an order 3 page. And similarly, order 3 page can be promoted to order 4 page because 2 order 3 pages are contiguous to each other. They can be combined, and now we have an order 4 page. The advantage it has is, let's say a task wants order, let's say order 3 page, and we have run out of order 3 pages. No problem. We simply look at the next list. Next list is order 4 pages. One order 4 page can be broken down into 2 order 3 pages. And that's what the subsystem will do. It will simply take an order 4 page and break it into 2 order 3 pages. This number will go up from 0 to 2. We'll allocate one of them, and we keep going. So that's how allocation works in terms of buddy allocator. Now, we allocate pages on the system for multiple uses. An obvious one is an application wants memory. It wants memory because it's doing, it wants to store data. Great. But there will be times when not all memory on the system is in use by applications or say even drivers, because anytime a task does IO, the driver will potentially allocate pages to bring in the data or send the data out to a device. And even after accounting for application use, kernel use, driver use, we may have free memory. And on Linux kernel, there is no such thing as unused memory. If there is any unused memory, kernel will try to use it up. And what it does with that free memory is it uses it for caching. So if you think about a task wants to read data from a file on a disk. Disk is a slow device. When the task requests data to be read from the disk, we say, okay, hang on, we are going to go read it from the disk and we'll get back to you when it is available. The task has to wait. And if we do it every time we have to go out to the disk, we are going to see fairly slow performance. So what kernel will do instead is every time it goes out to read the disk, it will read a few extra blocks from the disk and put them away in the page cache. So that the next time a task comes along and says, now give me the next block, kernel goes, aha, I already have it in the cache. I can give it to you immediately. Similarly, when you're writing data, same thing. Instead of writing to disk and waiting for that write to complete it, kernel will write to a page, a page cache, and then flush those pages out to the device later in the background. It may also use the page cache to buffer some of the data structures. For instance, if you do ls on a directory, the result of that ls lookup can potentially be cached because someone else is going to come along and do ls again on that same directory. Instead of going out to the disk to read the directory, we simply bring it back from the cache. So I can show the effect of this caching because it has implications. So here on my system, if I take a look at how my memory is being used, I've got about 32 gigabytes of memory. Of that, my applications are using only about 2.8 gig. And there's 20 gigabytes of memory free, because there is 8.8 gigabyte already in use in page cache. So let's do some IO and see how it affects the page cache. So I'm just going to read some data from the disk, put it out on a file. So we read about 391 megabytes, and you can see the cache usage went up, because what kernel did was it allocated pages from page cache and then brought the data in. It wrote that data from the disk back out to a file, but it leaves all that buffer data in the cache as long as it can. So this creates a problem for us. And the problem is, now kernel is using up all this extra memory for its own purpose, and an application comes along and says, I want 100 gigabytes of memory. Kernel has to pretty much say, hang on, I gotta go scan the page cache, see which pages I can free up, and then I'll get back to you. That introduces latency in the application. So kernel has a couple more tricks up its sleeve. We already addressed how memory is allocated. So now we can talk about how this memory is freed back again. So the tricks kernel uses, it runs two kernel threads, kswapd and kcompactd. These two threads, what they do is, let's talk about kswapd first. Kswapd in the background will wake up periodically, and it will take a look at page cache, and it will look at the age of the pages and makes determination about which pages are not really needed at this point. If it is the page is not needed, it will either discard the page if it can, or flush the page out to the disk, and then it will reclaim those pages, so that a certain minimum number of free pages is always available on the system. And that's what kswapd does. It will try to be as proactive as possible, trying to anticipate what's happening with the system and then free up more memory so that the next allocation is not does not go into a stall waiting for memory to become available. So we talked about how buddy allocator pairs up the pages by size that are multiple of 2. Well, that's where kcompactd comes in. What kcompactd does is it sits in the background and it scans all the currently available free pages, and it will see which ones are physically contiguous. If it sees 2 physically contiguous pages, it will merge them together into the next higher order page. And it just does this. It will create as many higher order pages as possible. So if it sees 2 order 2 pages, it will combine them into a single order 3 page, and so on. kcompactd can also move data around. So ML subsystem supports moving the data around, and if the data for a task is moved from one page to another page, all we have to do is go back in and update the page table entry for the virtual address to say, okay, now this virtual address, instead of pointing to this physical page, it's now pointing elsewhere. And kcompactd will move data around in order to create more and more contiguous free pages. And then it will compact them into higher order pages. Okay, so I hope how pages are allocated and then how they are managed in terms of free pages is mostly clear. So I'll move on to how the pages are shared. Okay, so now that we know how kernel keeps the address space distinct for the processes and keeps access safe, because each task has its own set of page tables, and its addresses do not collide with anyone else. The virtual address for each one of the tasks tells the MMU where its physical address is when the task tries to access its virtual addresses. And safety is ensured because MMU operates in the hardware. It has this page table. Every time it sees virtual address, it will ensure it gets the right physical address, and no 2 address spaces collide, and access stays safe. But now we get to a point where someone says, but I want to share data with another task. And we both agree that we want to share this task, so give us a mechanism to do that. That mechanism is actually fairly straightforward. if we go back and look at the page table entry, all page table entry does is it says for this virtual address and this virtual page frame number, you go to this specific physical page address. Well, we could have an entry for two separate tasks where those two entries point to exact same physical page. So for instance, in task one, we have a virtual address. The virtual address points to entry J in page directory, which points to a physical page frame number, which we combine with offset, get a physical page address. Task 2 can have a different virtual address, which then ends up pointing to entry K in the page directory, but this entry K points to the same physical page frame number. So we take that same physical page frame number, combine it with the offset from this address, and we get an address that goes to the exact same physical page. So now we have two tasks. They are using their own separate virtual addresses, but they end up going to the same physical page. And that's how we share pages across two tasks or multiple tasks. So let's take a look at how much space do we need for these page table entries, and what is the cost for all of this sharing. So let's take a look at 64-bit x86 architecture, where base page size is 4K. Each page table entry for a 4K page is 8 bytes. So 8 bytes for a 4K page, pretty small, no big deal, until we have a whole lot of them. So as I showed here, each task that's sharing a physical page has its own page table entry. So let's say now we have 1,000 tasks that are sharing a single page. That's something that's not at all uncommon. On big database servers, we actually see it out in the field where it's a large database, 200 gigabytes, 800 gigabytes, and then you've got thousands of tasks that are performing queries on that database. Obviously, all these tasks are going to share the memory pages for that database because they are operating on the same database. Let's say we have only 1,000 tasks that are sharing that single page in the database. 1,000 tasks times 8 bytes. That's already 8,000 bytes. So for a 4K page, we need nearly 8K of space just to store page table entries. Now let's try to scale it up. As we add more tasks, all of a sudden we need a lot more memory just to store page table than the amount of memory we have. So that's not a sustainable situation. And it so happens that we have actually seen it happen in the field where a system crashed, and after investigation, what we found was that looking at the number of shared pages, it was a 500 gigabyte system or so, and there was some 360 or 380 gigabytes of space allocated to shared pages. And we computed that the system needed another 800 gigabytes of memory just to store the page table. So we need a solution for that. It's possible to solve it. First of all, do we really need to keep these multiple copies of page table entries? That's what is causing the problem. Well, maybe we don't. If we look at a threaded model inside a task on a Linux kernel, you can have multiple threads that are part of that same task. And the tasks and all the threads within a task share the same page table entry. So you can have 5 threads inside a task or 5,000, doesn't matter. The number of page table entries stays the same because they all share it. Why they can share the page table entry? Because all of the threads inside a task share the same virtual address. When someone refers to a virtual address X, and another thread within the same task refers to virtual address X, they are talking about exact same address, exact same physical location. And they share the protection for each one of the pages as well. So great, it all works out. We can have any number of threads without consuming more space for page table entries. Why don't we do the same thing for tasks as well? Tasks are supposed to be independent. They have each task has its own address space, but what if we let them share their address space? And if they can share their address space, because they already want to share memory, right? So we let them share address space, and hence we let them share the page table entries as well. So there are still a few requirements, but if we can meet those requirements, we can save significant amount of space. Just in the previous example, we were looking at 8,000 bytes in page table space alone for a 4K page. That 8,000 bytes drops down to just 8 bytes if all of them could share the page table entries. And the requirements, of course, are virtual address has to be identical across these tasks that want to share. And just like threads inherently trust each other. They're all part of the same task. They trust each other in terms of, you are not going to do something bad to corrupt my data. Well, shared memory, that's usually the case. A task doesn't share its memory with a task it doesn't trust. But if we have that right level of trust, we can share page table as well. So in order to do this, I have a proposal, and it's a new mechanism which I call mshare. It's an opt-in mechanism because of the conditions that exist for two processes to share page tables. They have to trust each other. And so we don't want to do it transparently without task knowledge. The task has to explicitly choose to share its page tables. So the way it works is, a task says, I have got this part of my address space that I want to share with other tasks. And it tells the kernel. Now, kernel keeps track of which address range is shared. And then another task comes along and it says, I want to share that address space that was shared by this other process. Kernel simply makes sure that all the right permissions are in place. The other task has the right to share this address space. And then it will set up a shared page table so that both addresses can now start sharing that space while sharing a page table. So trust between those two tasks, or all the tasks that are sharing the page table, is very important. And that's why I want to make it an opt-in mechanism. So how does it work? I have created a design. I've created an implementation. What that implementation does is it adds a new in-memory file system. So Linux kernel supports in-memory file systems where the file system only exists in memory. You reboot the system, it's gone, it is recreated. And there's a new file system is called msharefs. So after the system comes up, you mount the msharefs onto a mount point, which the best place for that is sysfs mshare. Once a file system is mounted, all a process has to do is create a file on that msharefs file system. When it creates a file there on that msharefs file system, kernel says, aha, now we know we are going to create a shared page table address space. And then a task can simply map that file it just created on the msharefs file system and give it an address range in its mmap call. So now the kernel knows a shared address space exists, and here is the extent. It starts here, ends here. And now the task that is started the sharing can start mapping any objects in that address range. Objects can be anonymous data it creates and just writes to those pages. Data can be a mapped file, for instance, or a network mapped data. So any possibilities, but it can map any objects it wants in that space. Now, how does someone else get access to that? A client process simply opens that file that exists on that msharefs. It opens that file and mmaps the file descriptor it gets back. Once it mmaps the file descriptor, that tells the kernel, now we are sharing address space between these two tasks. And then kernel will set up the shared page tables and all of the right plumbing underneath. And now we're off and running. All these tasks, more tasks can come in and keep mapping that space. And all of these tasks are now sharing that space, which means a write by one task becomes visible to everyone else. A change in attribute of a page becomes visible to everyone else. So that's the important part of sharing page tables, because not only you are sharing the data, you are also sharing the attributes of the page. And say at some point it's done with the sharing. We want to tear down this entire shared address space. Fairly straightforward. You just call unlink on the file that was created under msharefs, which says when no one is using this region anymore, just tear this down. And that's what kernel will do. It keeps tracking. It has got ref counts to keep track of how many processes are using the shared region currently. When no one is using it any longer, it will tear down that space. Okay, so I'm going to wrap up in a couple of minutes, and then if we have any questions, I'll take those questions. Where this work is right now, I sent out RFC patches earlier this year. There was a lot of discussion, feedback, so that resulted in refinement of the API some, and that based upon that feedback, I created a version 1 patch, which I sent out in early April. There was further discussion, ideas on how much further the API can be refined and simplified. So the API I just talked about is the result of discussions from the V1 patch. I'm working on the next version of the patch. It's mostly done. I have just some more cleanup to do, and I'll be releasing the next version 2 of the patch in the coming days, probably in the next couple of weeks or so. That's what it is. We'll continue with the process of reviewing these patches and even the API and implementation in the upstream. At some point, hopefully, it will look good enough and it will go upstream into the kernel. Okay, so that's all I have. Any questions?
There is a question on chat. Can you see? I can read it out too. Steve is asking, could you discuss mapping of tasks to thread and threads to process and how that relates to page tables?
Okay. So we generally talk about process and threads. Threads are parts of a process. What Linux kernel uses, it uses a concept more of what it calls just tasks. Task is just a container. A task can contain a process or a thread. So that's why I keep referring to tasks and process, and somewhat interchangeably, even though task is a container. So the way mapping works is when a task is created, when a process is created inside a task container, we create a page table entries for its entire address range and populate only the ones that we need. And then any thread that is created will have its page directory pointing to the page directory for the main task. So for instance, if I go back here, let me bring up that picture, this. So everyone that wants to access physical memory will have a page table. So a thread, simply its page directory points to the page directory for the main task. So as a result, they all share exact same page table at every level. Make sense? Okay, and then looks like we have, okay, awesome. By the way, that's a good point. Shaw mentioned that I had presented this idea, the mshare idea, on how to share page tables at LSFMM very recently. We had a big discussion, a lot of good feedback. Generally, people like the idea because it has real significant impact on system performance in terms of saving space. And even API, where it is today, everyone seems to be okay with the API for the most part. Is the implementation where we are still hammering things out, because if you think about it, sharing page tables across tasks, it sounds scary. What one task does affects someone else, and you could stomp on each other's page attributes, not just data. So it sounds scary. So a lot of security mechanisms have to be in place to ensure we don't have rogue processes doing bad things and bringing down the entire system. And I'm working through the process of ensuring that all of the access to the shared page table is safe and is in accordance with what the system designer wants to happen on the system. So we have multiple levels of security, file-based, and then I'm also thinking about adding security keys. So good discussion at LSFMM, lots of feedback on how this can go wrong. So I'm working through the process of making sure we take care of all of those things. So I see another question. Is there any safety benefit in using mshare? The safety benefit, and this actually came from the database guys. One of the things the database guys wanted was they wanted space saving that page table sharing brings, but they wanted to be able to change the page attribute. So for instance, there is a segment of database that they wanted locked against any writes. Doing that when you have distinct tasks that each has its own page table is non-trivial. You have to send messages to every process, then wait for every other process to implement that permission change. What if one could simply change permission and it changes instantly for everyone else? And that's what page table sharing brings. So what is safety benefit? That's what it is, that you can change the attributes of the shared data range and protect any part of the shared data range instantly by simply changing the page attributes, and it becomes visible to everyone right away. Okay, so hopefully that answered the question. Okay, I see another one. In safety embedded systems, isolation between ASIL components and QM components is a must, which is done by page table. But what if corruption happens in the page table? A corruption in the page table is, of course, a truly bad thing, because you could potentially be pointing to anywhere in the memory. How do you protect against page table corruption, which applies whether we are sharing or not? It doesn't really matter. Page tables are privileged data structure. So in order to change anything in the page table, the process must be executing at the proper privilege level, which is the highest privilege level. And privilege levels are maintained inside the processor in a register. So anytime a task is running, which privilege level it is running with is maintained in that register. For it, a task is always started at the user privilege level, which is the lowest privilege level. A task can escalate its privilege by only by using certain very specific paths. System call is one of them. System call is handled through a hardware trap, which causes the current privilege level to be changed to the highest privilege level potentially. Although that's not a given, because some systems use multiple levels of privileges and they do escalation more slowly than jumping to highest privilege. But nevertheless, let's assume a task executes a trap by making a system call, which escalates its privilege. Now it can access kernel data structures, and page table is part of the data structure. But now the control is entirely in the hands of kernel at that point. We are executing kernel code, not user code anymore. And before the control is returned back to the user code, kernel will actually reduce the privilege. It will drop the privilege back down to user privilege and then transfer the control over to user space code. So page table is just another kernel data structure. There are so many kernel data structures that need to be protected against corruption. And it's usually done by using the privilege levels. Okay, so hopefully that made sense. Any other questions? Okay, I don't see any questions on chat. So I think we are done.
Great. Thank you, Khalid, for giving us this very detailed talk. And thank you everybody for participating and asking questions. And as I mentioned, this is recorded, so we'll also distribute this to the ELISA community. So thanks again, and take care.
Right. Thank you, everyone. I appreciate your time.
Thank you.
You're welcome. Okay, bye.
Bye.